Welcome students. Here we will study digital image processing with the code number EC703A. Myself Kaushik Pal, Assistant Professor, Department of Electronics and Communication Engineering, Guru Nanak Institute of Technology. Today our topic is types of pixel neighborhoods. What does that means? We already know what is pixel. Pixel is the smallest entity of any digital images. That means collection of pixel can be termed as digital image. If we want to design a building, we require small bricks. Now these bricks may be considered as the building blocks of the entire building. If we want to design any type of memory device, in that case we require lots of flip-flops. Those flip-flops are known as the smallest elements or building blocks of memory devices. So pixel is also the smallest entity of any digital images. Pixels has two parameters. One, its positional informations or its coordinates, that means where it is situated in the particular image, and the intensity value, that means how much light is getting reflected from that particular pixel and coming to our eyes, that is known as the intensity level or the brightness level. Now image sampling is very much important. These two type of sampling can be done. One is rectangular sampling, another is hexagonal sampling. Rectangular sampling is very common and popular. In most cases, images are sampled by laying a rectangular grid over an image. In case of hexagonal sampling, this is an alternative sampling scheme which is also shown here, but I have already mentioned that rectangular sampling is much more popular than the hexagonal sampling. Three types of pixel neighborhoods can be seen here. One is 4 connected, another is 8 connected, another is 6 connected. For hexagonal sampling we should use 6 connected neighborhood, but in case of rectangular sampling we may use either 4 connected or 8 connected. Pixels may have different type of pixels near to it, which are also known as neighbors pixels. So if we want to see in pictorial representation, here we can see these three types of relations. One is 4 connected, another is 8 connected, and the last one is 6 connected. So for 4 connected, there are pixels having 2 horizontal pixels and 2 vertical pixels just adjacent to it. In case of 8 connected, it should have 2 vertical pixels, 2 horizontal pixels, and also with 4 diagonal pixels. So all these 8 pixels are linked to that particular pixel which is known as 8 connected. And if we consider hexagonal case, that means 6 connected pixels are there. So these are the basic relationship between all the pixels, or these also known as types of different neighbors or neighbor of the pixels. Now if we want to measure the distance between two pixels, we can also measure that. In that case, 3 types of these distance measurements are there. One is D4 distance, another is D8 distance, and the last one is Euclidean distance. D4 distance is also known as city block distance. D8 distance is also known as chessboard distance, and the last one is Euclidean distance. The formula is given here. Now if we consider any two pixels, one is P and another is Q, So we can measure the distance between that particular P and Q. Here, if pixels P and Q have coordinates xy and st respectively, then we can see three different formulas to find out their distance between them. So here xy is the coordinate or positional information of the first pixel, that means pixel P, and st is the coordinates or positional information of the second pixels, that means Q. So if you want to calculate the d4 distance or CT block distance between P and Q, we should use the equations, second equations, d4 PQ equals to mod of x minus s plus y minus t. So this is the formula by which we can find out the d4 distance. To calculate the chessboard or DS distance between P and Q, we should follow the formula d8 PQ equals to maximum of x minus s y minus t. So we have to calculate the difference between x minus s, and we also have to calculate y minus t. Now which result is the maximum, that will be the d8 distance. If we find out Euclidean distance between P and Q, then we have to calculate the square of the difference of x minus s and y minus t, and after addition of them we have to take the square root. So by that we can have the distance which is known as Euclidean distance. So these are the three formulas by which we can find out the different or three types of distance measure of the pixels, which are known as d4 or CT block distance, d8 or chessboard distance, and Euclidean distance. Now here we can see that results of d4 and d8 distance. The pixels with d4 equals to 1 are the 4 neighbors. Pixels with d8 equals to 1 are the 8 neighbors. So if we consider here the 0, that means it should have all the pixels 2 vertical and 2 horizontal with 4 diagonal are known as 8 neighbors, where in the first image we can see there are 2 vertical and 2 horizontal, so they will give you the results of d4 neighbor distance. Now if we take a solved example, or if we take an example and we should solve that, so we can see, let V01 compute d4, d8 and dm distance, that means the corresponding Euclidean distance between P and Q. Here we have taken the 0, 0 position is the corresponding Q, and the corresponding, we can see this is 0, 1, 2, 3. So this is 3, 3. So the coordinate of P is 3, 3 and the coordinate of Q is 0, 0. So we have to calculate all the three distance between this point and this point. So if we want to here computation of Euclidean distance, if we want to just calculate the Euclidean distance for the coordinates of Q and P, we have to use the formula x1 minus x2 square plus y1 minus y2 square to the power half. That means y1 is the coordinate of the corresponding Q, and the x2 and y2 is the coordinate of P. Now here the coordinate of Q is 0, 0 and the coordinate of P is 3, 3. So from there we can easily calculate here the Euclidean distance is 3 root 2. Now if we want to calculate the d4 distance between the same P and Q pixels having 0, 0 and 3, 3 coordinate, the value should be d4 equals to mod of 0 minus 3 plus mod of 0 minus 3, that means 3 plus 3 equals to 6. Now computation of d8 distance equals to d8 equals to maximum of 0 minus 3, 0 minus 3. So here in both the cases, as the result is 3, so the D8 distance will be 3. So in this example we can see, if we want to just calculate the distance between two pixels having coordinates 0 0 and 3 3, so the result of D4 distance will be 6, the result of D8 distance will be 3, and the results of Euclidean distance will be 3 root 2. So this is the solved example, or if any example will be given this to measure the distance, this can be used. So this is a very important example. Moving forward to the next slide, adjacency, connectivity, regions and boundaries. So as already we mentioned, two types of adjacency may be there. One is 4 adjacency. Two pixels P and Q are 4 adjacent if Q is in the set of N4 P. And for 8 adjacency, two pixels P and Q are 8 adjacents if Q is in the set of N8 P. Connectivity, let S represents a subset of pixels, then two pixels P and Q are said to be connected in S if there exists a path between them consisting entirely of pixels in S. The set of pixels that are connected to each other in S is called a connected component of S. Now, what do we mean by path? A path from pixel P with coordinate xy to pixel Q with coordinate st is a sequence of distinct pixels with coordinates. This path is also known as curve. So it should start from x0, y0, x1, y1 up to xn, yn, where x0, y0 equals to xy and xn, yn equals to st, and pixels xi, yi and xi minus 1, yi minus 1 are adjacent for the range I is greater than 1 and greater than equals to 1 and less than equals to n. In this case, n is the length of the path. If x0, y0 equals to st, the path is a closed path. We can define 4 or 8 paths depending on the type of the adjacency specified. What do you mean by region? If R be a subset of pixels in an image, we call R a region of the image. If R is a connected set, it must be connected. Now what is the boundary? The boundary, also called border or contour of a region R, is a set of pixels in the region that have one or more neighbors that are not in R. Now from these examples, here we can see an arrangement of pixels is given, and pixels that are 8 adjacency, that means adjacency is shown by the dashes line in case of the second image, and for the third image this is the n adjacency has been shown, and for the fourth image two regions that are adjacent if 8 adjacency is used, and the middle image in the second row is the circle point is part of the boundary of the one valued pixels only if 8 adjacency between the region and background is used. The last images shows the inner boundary of the one value region does not form a closed path, but its outer boundary does. So here we can see the corresponding outer boundary is all have the similar value of 0, so this can form a closed path. Here we can see a closed path. So these are the different examples of where we can see different type of adjacency, connectivity, regions and boundaries. Now types of image operations. Three types of image operations can be done. So they are also known as operation domain. So first one is the point operation or point domain. The second one is local operations or local domain, and the third one is known as global operation or global domain. So here if we just look this table having three columns, one is operation, then is characterizations, and the last one is complexity or pixels. So for point processing, the output value at a specific coordinate is dependent only on the input value at that same coordinate, and the complexity of per pixels is constant. Whereas for local processing or local domain, the output value at a specific coordinate is dependent on the input values in the neighborhood of the same coordinate, having the complexity of pixel is per pixel is p square. And for global domain or global operations, the output value at a specific coordinate is dependent on all the values in the input image, and the complexity per pixels here is n square. So this is the different types of image operations, which is also known as operation domain. Now types of image operations is given here in pictorial format. Three types of image operations are there. One is point processing, and that is local processing, and the third one is global processing. So here A and B are two sets. If we compare pixel to pixel having these two different sets, then it is known as point processing, that means point to point processing. Local processing means pixels of local area with another pixels, which is known as local. And if entire image, any pixels of the entire image is actually compared with another sets of pixels, that is known as global operations. Now different type of examples we will see here for types of image operations. So this is the pixels operations, where we can see three figures where the contrast has been either enhanced or decreased. So for the first image, we can see this is a example which has been taken of low contrast image. The second one is medium contrast, and the last one is high contrast. So here we can see these three images has these three visual look, where the low contrast image is not so clear, but if we just enhancing or we stretch the contrast, the quality of the image getting better and better. So this is one type of operations which is as pixel to pixel comparison is there. So that's why this is known as pixel operations. This one is the types of operation which is known as local operation. So here local averaging using neighborhood processing, we can see the procedure is illustrated in A and B figure for a rectangular neighborhood. So if we just compare these type of images, the first images with the second images, so for we can see the second the third image is the corresponding angiogram, and the last image is the result of using this corresponding m equals to n equals to 41. The images are has all the same size, that means 790 cross 686 pixels. So this is the operations of local processing. Whereas other also examples we can see here, we are using some images of the galaxy. So here these images we can see, if we choose all the images are different type of noisy images, and the level of noise are different. So from there we can see the first image has much more noise, whereas the last image is almost no noise. So we can also remove different type of noise effects using these local operations. also. Now lots of arithmetic operations can be done. In this example we have used shading corrections. That means the shade has been corrected, different type of shades has been corrected here. So for the first example here we can see three different images. The first image is the shaded ACM image of a tungsten filament and corresponding support magnified approximately 130 times. So we have magnified these images, tungsten images, the corresponding filament 130 times. Now the corresponding shading pattern has been given in the corresponding B image. Now if we just take a product of this A by the reciprocal of corresponding B, we can have the corresponding results in the C. So the C image is nothing but the product of A by the reciprocal of B. So we can see here also the quality of the last image is getting good, and we can see it has been enhanced. So arithmetic operations can also be done by enhancing the quality of the image. So other examples are also given here. So here we have taken an example of a digital dental x-ray. The first A images is x-ray of some corresponding tooth. Now the second one is the ROI mask for isolating teeth with the corresponding fillings. So here some of the teeth having fillings and some of the tooths are normal. So if we just separate out all those corresponding region having the filling, so we should use the second images. Now if we corresponding take a product of the image A and image B, then we can have the image C, where we will just find the corresponding teeth with filling. So other operations are also here shown. So you can see the different type of logical operations has been given here. Though we have corresponding these. For the first one, white portion is in the black portion, which is known as corresponding A, and if we just take the complement of that means not A, so we perform the NOT operations, then the outer side will be white and the inner side will be black. So white portions will be turned into black and black portion will turn into white. So this is just the NOT operation. Now if we consider two different region and take AND of them, so the common area will be corresponding white and all the other portions will be black if there is two different areas. Now for the third case we are taking the OR operations. That means we have taken two images and we are finding out the A region or B region. So getting the OR value of A and B, we should have the common of A and B. So it is resulting here. Now if the next example is AND NOT, that means if we take the and then perform the NOT operations, then the result will be like this. And the last one is XOR operation. So if we just took the A and B XOR functions, if we took A XOR B, the result will be shown here. So this is all the operations having logical operations. So we have seen some arithmetic operations also, and here we can also see some logical operations on the image. Now these are the different type of operations is illustrated here. Set operations. So we can have the union value. So here two regions are there, one is A and there is B. So we can have the difference, we can have the intersection, we have the union. So different types of results will give you the different values. So here two sets of coordinates A and B in 2D shapes has been given. The union of A and B has been taken in the next images. In the third images, the intersection of A and B has been taken, and for the fourth image, the complement of A has been taken, and for the last images the difference between A and B has been taken, and these has been given in either clear white area or shaded area. So these are the different set operations of the image, or having two different areas. Now the set operations has been shown with some real-time examples here. So from here we can see that in this figure set operations involves grayscale imaging. First one is the original image, and the second one is the image negative obtained using set complementations, and the third images is the union of A and a constant image. So here we can see we can use these different type of set operations to find out different areas or for our different purpose to enhance the quality of the image. Now these are the geometrical or geometric operations, that is also known as transformations. So different type of transformations can be done. One is known as identity, next is the scaling, then rotations, then translations, then shear horizontal, then shear vertical. So all the examples has been given. So this is the different type of transformation nature, and the corresponding coordinate equations and examples has been given here. So all the corresponding identity, scaling, rotations, translation, vertical shearing and horizontal shearing is also given here. So this is types of image operations. So from the spatial domain, if you have some input or image function fxy, that will be given in different type of transformation block. Now after the transformation block, it will be converted into TUV, then the particular images in transform domain will be faded in different type of operations. Now after operations, the inverse transformations has been taken to convert the again image from transform domain to its equivalent, this spatial domain. Now this transform operation and inverse transform, these lies between transformation domains, where fxy and gxy lies in spatial domain, where fxy is the image functions before processing and gxy is the image function after processing in the transformation domain. So this is the general approach for operating in the linear transformation domain. Here types of image operations, space transformations has been given, where you can see the first image corrupted by sinusoidal interference, and for the B images magnitude of the Fourier transform showing here in the energy responsible for the interference. C is the mask used to illuminate the corresponding energy burst, and the last images is the result of computing the inverse of the modified Fourier transform. So you can see the first images which was corrupted by sinusoidal interference is much more clear at the last images. So if we compare the first image with the last images, or first image with the fourth image, we can see the difference. So fourth image is much more clear. So we can see here, if we use different type of space transformations, so type of these images may be enhanced, or the quality of the image may be much more better. So these are the different types of image operations which I have already mentioned. One is corresponding point operation, another is local operation, and the last one is global operation. So these are the image operations. Thank you very much, students. Hope you have learned all these things, and if you have any queries, you can ask. Thank you very much.